Welcome to Calculus. Today we will investigate how to find general solutions of differential equations by separation of variables. We'll take a look at three total examples. Our first example is given to us in Leibniz notation. We've got dy over dx equals -1 over sine y. Our goal is to find the general solution for this differential equation, and as I can see in my title, my strategy to do so is going to be by separation of variables. So I'm going to start, and essentially I want to group any terms here that involve y on the left side, and I want to also group any terms, including differentials, that involve x on the right side. So initially, what I'm going to do to this dy dx is I'm going to multiply by dx to cancel on the left, and dx is going to show up to keep the balance there on the right side. At that point, what I've got is dy equals -1 over sine of y times dx. So at that point, I've separated my dy dx into two different parts. I have one more factor there on the right side that needs to move over to the left because it involves y. So here on the right side, I'm going to multiply by sine of y to cancel 1 over sine y. And with that multiplication, I have separated my variables. So at this point, I've got everything that involves y on the left, everything that involves x on the right. So just to record, we got sine y dy equals negative dx. Once I've separated my variables, at that point, what I want to do, because I am interested in solving for y, is I want to integrate both sides of the equation. So we'll do so. I want to integrate the left side, which is sine y dy, and I also want to integrate the right side, negative dx. So we integrate using our normal integration strategies. So if I've got sine of y, I just want to consider what my antiderivative for that would be. So I know that cosine has the derivative of negative sine y. So if I'm looking for just positive sine y, my antiderivative is going to be negative cosine of y. And we'll record that there on the left side. On the right side, the integration is very simple. I can think of this as a -1 dx. So the right side is going to integrate as negative x. And because this is an indefinite integration, I have to include the constant of integration plus c. So at that point, we're very close to solving for y. I just need to do two more steps. I need to cancel this negative on cosine of y. So I'm going to do so by multiplying by -1, and that'll resolve as a positive. We'll also multiply the right side by -1. So at that point, what we've got is going to be positive cosine y equals, I got to distribute this -1. It'll make my x positive. And I don't really know the value of c, so whether it's negative or positive to begin, I'm just going to let the -1 absorb into the c value, some constant. I don't know what it is. My last step is to cancel the cosine function there on the left. And I can do that by applying inverse cosine. I'll apply that on both sides. And that basically solves our equation. That's going to cancel my cosine. So at that point, I've got simply y on the left. And on the right side, I've got inverse cosine of the angle x plus c. Once I've gotten down to a solution that has y equals everything else on the far right side, I am done. We've solved our differential equation. Let's take a look at a second example that involves more parts. So this is dy over dx equals x squared divided by e to the power of 2y. Initially, I want to do the same thing as in my first example. I want to separate my variables. And again, I'll put everything that involves y on the left side, everything that involves x on the right side. Good place to start is to multiply the left by dx. It'll cancel there. I'll multiply the right side by dx. So next step I've got is going to be dy equals x squared dx, all divided by e to the power of 2y. I see I do need to cancel the division by e to the power of 2y. So on this right side, I'm going to multiply by that factor. It'll cancel there on the right. And I'll also multiply the left side by that same factor to keep the balance. So at this point, I've separated my variables. On the left, we've got e to the power of 2y dy equals x squared dx. And at that moment, once I've separated the variables, one side of the equation and the other, I'm ready to integrate. So we'll apply our integration to both sides. And at that point, I need to think about what the antiderivative for e to the power of 2y would be. Definitely, it would involve that same expression, e to the power of 2y, but I definitely would need to apply chain rule here, which when I took the derivative would involve a multiplication by 2. To cancel that out, I'm going to put a half on my antiderivative. That helps me to integrate here. So this integration of e to the power of 2y dy is going to be half e to the power of 2y. Integration of the right side is fairly straightforward. That's just a x squared. So using my basic power rule, that's going to integrate to 1/3 x cubed. And again, I'll include plus c. So at that point, again, I want to solve for y. That's really my goal with all of these equations. So I need to employ some of my algebra strategies to do so. I'm going to multiply by 2 to cancel this half. And we'll multiply the right side by 2. So now we've got e to the power of 2y equals, if I distribute the 2/3 x cubed. And just like we did with our negative in the previous example, 2 times c will just still be another c, some constant that we don't know. So with this example, I see that my y is currently in a way trapped in the exponent. It's e to the power of 2y. To solve this equation, I do need to get that y value down on the main level. So to do so, I'm going to apply the natural logarithm. And that'll do that exactly what we're looking for. By the log rules, it'll take that power and move it out front as a coefficient. So my next step, what I'll have on the left there is 2y times natural log of e. And natural log of e is going to reduce down to just 1. I do need to apply natural log to this right side as well. So I do need to put natural log 2/3 x cubed plus c. And that's what we'll see on our next step. We just have one step left to solve this equation, and that's to cancel the 2 on my y. In fact, let me bring that up here so we can see it clearly. So we have at this point 2y equals natural log 2/3 x cubed plus c. So our last step is going to be to multiply by half. That'll cancel the 2 there on the left. And that'll give us a good solution for this differential equation. Y equals half natural log 2/3 x cubed, plus c. Our third example does not use the Leibniz notation. It's got the prime notation. So our third example here, number 7, says y prime equals yx squared plus yx. So not only does it use a different notation for the differential part, I see on the right side, I've got both x's and y's. So my strategy still is to separate variables. So I want to do two things initially. The first is I want to translate y prime to dy dx. I want to take it back to the Leibniz notation because Leibniz notation works well for separating my differentials. Second thing I want to do is I want to factor out the common y on the right side. So both terms have y as a factor. If I factor it out, I'll have x squared plus x. So with those two changes, I can clearly see how I can separate my variables. On the left side, I can apply that same strategy, multiplying by dx to cancel dx and move it permanently to the right side. So at that point, we'd have dy equals y times x squared plus x dx. Only one more variable to move. I see I've got this factored y here on the right side. It's out of place, so I need to divide it off. And at that point, we're ready to integrate. I've got dy over y on the left, so those are my y terms, equals x squared plus x dx. And at that moment, our variables are separated. Once I've got that the case, same as before, I'm going to integrate both sides. So integration there on the left, if I consider that I've got 1 over y dy, the antiderivative is definitely going to be the natural log of y. So we'll integrate. In fact, that's going to be natural log of absolute value of y. So that's our left side. On the right side, the integration again follows our basic power rule. So integrating x squared, that's going to be 1/3 x cubed. And integrating x is going to give us 1/2 x squared. And again, plus c. So again, once I've got it past the integration, I want to then solve for y using algebraic strategies. So I see on the left, I've got the natural log of y. To cancel the natural log, I'm going to exponentiate. I want to raise e to the power of natural log of y. And I'm also going to raise e to the power of 1/3 x cubed plus 1/2 x squared plus c. Why do I want to do that? That, for me, gets my y out of the natural log. E to the power of natural log of y is going to simply be y. And on the right side, I have that mostly the same. It's going to be e to the power of 1/3 x cubed plus 1/2 x squared. But I want to revert using my exponential rules to say that this is times e to the power of c. I'm just splitting the addition in the exponent into multiplication of the same base to that power. Why do I do that? That allows me to bundle e to the power of c. If you recall, e is just a constant, 2.71, so forth. If I raise that constant to a constant, that's just a new constant. So my final answer here is going to be y equals c as a coefficient, e to the power of 1/3 x cubed plus 1/2 x squared. And that completes my solution. Thank you for joining for these 3 examples of solving differential equations by separation of variables. See you soon.